Hi, today we're going to talk about eigenvectors and eigenvalues.
These concepts are used in many fields of physics, however they might prove troublesome to some physics students.
We'll try to shed some light into what they actually mean and their applications, as you will encounter them several times during your course.
So what is an eigenvector?
First, one should understand what a linear transformation means,
and how that may be represented by a matrix.
A transformation is a mapping between one initial vector space to another.
The transformation is linear if the new basis can be represented as a sum of the original basis times some coefficients.
A matrix can be used to denote a linear transformation.
Every column of the matrix represents where the basis vectors will land after the transformation.
So for example, the matrix 0, 1, minus 1, 0 transforms a vector space when applied to any vector.
Our I vector will land on 0, 1 and our j vector on minus 1, 0.
This particular example represents a 90-degree rotation.
As we transform the space, other vectors will be affected and land on different points.
Most vectors will be moved off their span, that is, the line that passes through the vector.
Some others will remain on their span, being scaled down or up.
These vectors are the eigenvectors.
And the factor by which they are scaled is the eigenvalue.
For any given matrix, we can determine its set of eigenvalues.
Each eigenvalue has a corresponding unitary eigenvector.
And a multiple of this vector still verifies the equation.
When calculating the eigenvalues of the matrix, we get a polynomial equation of the same degree as the number of dimensions of the space.
In our 2D space, we would have a quadratic equation.
From this, we can see how some transformations have two eigenvalues, like in the previous example.
Others, like a shear, only have one.
Some have none, like a rotation in 2D space. Every vector is rotated, so none remain in their span.
Some might even have an infinite number of eigenvectors.
The simplest example is scaling the space. All vectors are scaled and therefore they all remain within their span.
We've seen what eigenvectors are, but what are they useful for?
Many areas of physics use eigenvectors.
Even you may have used them without noticing.
The equation of a harmonic oscillator is an equation where the solution is an eigenvector.
The second derivative can be expressed as an operator represented by a matrix.
By differentiating the function twice, we get the same function multiplied by a scalar.
That is an eigenvector, and they can be used to solve the normal modes of oscillation.
We see how the solution to the harmonic oscillator is a sinusoidal wave.
If we plot both the position and acceleration, the graph of the acceleration is simply the result of scaling the graph of the position.
This is because of Hooke's law, where the force is proportional to the position.
The eigenvector arises from that proportionality.
Other examples of eigenvectors are found in rotations in 3D space.
When the 3D space is rotated, the only vector that is not affected by this rotation are the ones that lie on the rotation axis.
This is useful because we can represent a rotation with a vector instead of using a matrix.
Even in quantum physics, they're used a lot.
To measure properties of the system, like the momentum or the energy, we apply operators to the wave function.
The eigenvalue has a physical meaning. It is a desired property.
In this case, the eigenvector is replaced by an eigenfunction,
Known as the wave function.
Which can be used to obtain the probability of a quantum system being in a particular state.
Thanks for watching, we hope you enjoyed.